All right, so today we're going to play detective. Our case, a massive construction crane. Now, it looks like it's just sitting there perfectly still, but it's actually in the middle of this invisible, high-stakes battle of forces. And our job is to uncover these hidden forces and figure out exactly how this thing is holding on without ripping itself right out of the wall. All right, let's get into it.
So here's our scene of the crime. We're talking about a 1,000-kilogram crane, and it's lifting a whopping 2,400-kilogram crate. It's only anchored to the wall at two little points, A and B. So the big question is, what in the world are the invisible forces at A and B doing to fight against all that weight, nearly 3,500 kilograms of it, pulling straight down? How is this wall even holding on?
Right, so any good detective knows the first step, you got to identify all the key players. For us, that means mapping out every single force, the obvious ones, and yeah, the hidden ones too. Let's start with the heavy hitters.
First up, we've got the crane's own weight. It's 1,000 kilograms, and that's pulling it down, from its center of gravity all the time. That's a huge force we absolutely cannot ignore.
And then, of course, you've got the main event. This 2,400-kilogram crate. I mean, this is the whole job, right? And it's adding this massive downward pull that the wall somehow has to deal with. Okay, so this is where the real mystery kicks in. See, with all that weight pulling down, for the crane to stay put, the wall has to be fighting back at points A and B with equal and opposite forces. And those are what we call reaction forces. They're the invisible suspects we're going to unmask. Okay, so in physics, you don't just guess, right? We draw a map, a special kind of map that shows every single force involved. And honestly, getting this map right is probably the most important step in cracking this whole thing. All right, so let's start with a simple sketch of our crane. You can see the two spots where it's anchored to the wall, A and B, and we've got the center of gravity marked at G. Now, let's start putting our forces on this thing. First up, let's pencil in the forces we actually know about. We've got the crane's own weight, that's the 1,000 kilograms, pulling straight down from its center of gravity, G. And then, all the way at the end of the arm, you've got that 2,400 kilogram crate also pulling straight down. Now let's look at our suspects at the wall. The joint at point B, that's called a rocker. Think of it like a skateboard wheel pressed up against the wall. It can push straight out away from the wall, but it can also roll up or down freely. What that means is it can only give us a horizontal push. It has zero, and I mean zero, vertical support. Now, point A, that's a whole different story. That's a pin joint. This thing is the real workhorse of the whole setup. It's locked in place, so it has to fight forces from all directions to keep the crane from moving. So to make it easier to figure out, we break its total force into two pieces. A vertical part, we'll call it AY, and a horizontal part, AX.
And there you have it. What we've just put together is called a free body diagram. This is our complete map of the scene. Every single force is now accounted for. Literally everything we do from here on out is based on this one drawing.
All right, so we've got our map. Now we need the rule book. You see, because this crane isn't moving, it's not falling, it's not spinning, it's in a state we call static equilibrium. And to stay that way, it has to obey three and only three totally unbreakable laws of physics. And here they are. Super simple. Rule number one, all the forces pushing left and right, they have to perfectly cancel each other out. Add up to zero. Rule number two, same thing for the forces pulling up and down. They've got to cancel out too. And then there's rule number three. And this is the secret key to the whole puzzle. All the turning forces, the forces that would make the crane rotate or spin, have to be balanced too. Physicists have a special name for this, moments. This seesaw, it's the perfect way to get your head around that third rule about moments. See, a moment isn't just about how much weight you have. It's about the weight times how far away it is from the pivot point. A lighter person can balance a much heavier one just by sitting further out. And that simple idea, force times distance, that's going to be our secret weapon for cracking this case. Okay, we've got our map, we know the rules, it is time for the breakthrough. We're going to take those three laws of equilibrium, apply them to our diagram, and finally solve for those mystery forces at A and B. So here's our four-step plan of attack. Step one, and this is the really clever part, we're going to look at all the turning forces, the moments, around point A. Now why A? Well, think about it. Any force that acts right at the pivot point has a distance of zero from it, so it can't create any turning force. This is a brilliant move because it lets us completely ignore those two tricky unknown forces at A, AX and AY, just for a moment. Step two. Now that A's forces are out of the picture, our moment equation has only one unknown left, that force at B. So the clockwise turning from the two weights has to be perfectly balanced by the counterclockwise turning from the push at B. We do a little bit of algebra and boom, we can solve for B. Step 3. And once we know B, the rest is like a domino effect. It's super easy. We just use rule number 1. All the horizontal forces have to add up to 0, and that immediately gives us AX. And finally, step 4. We use rule number 2. All vertical forces add up to 0 to find our very last unknown, AY. It's just a beautiful, clean, logical process.
All right, the math is done. We've applied our 3 rules. We've followed our strategy to the letter, and the verdict on our invisible suspects is in. Let's see what we found. And here they are. Get this, the wall at point B is pushing outwards with a massive 107,000 newtons of force. So to stop the whole thing from sliding sideways, the pin at A has to pull back with the exact same force. And as if that's not enough, that same pin at A is also holding up the entire weight of the crane and the crate. That's over 33,000 newtons pushing straight up.
But what does a number like 107,000 newtons even mean in the real world? It's hard to picture. Well, check this out. That horizontal force at both A and B, that's like the wall having to push or pull with the weight of about 11 small cars. That is a staggering amount of force, and it's all happening completely unseen, right inside that connection to the wall.
And you got to remember, this isn't just some abstract problem from a textbook. This is exactly what structural engineers do every single day. This is the math they use to figure out, how big the bolts have to be, how thick the steel needs to be, how strong the welds have to hold. Getting this math right is literally the difference between a crane that stands for decades and a catastrophic, disastrous failure.
So we did it. We've cracked the case and unmasked the invisible forces keeping this crane perfectly balanced. But, solving for the forces, that's really just step 1. It actually leads to an even bigger question. Now that we know just how incredible these forces are, how do engineers pick the right materials, the right pins, the right beams that can actually handle that kind of stress day in and day out without snapping? And that, my friends, is where the next level of engineering really begins.